This video is going to cover the solutions to the tutorial problems for topic 8, how do glasses work. In this problem, we're told that the visible spectrum covers the range from 380 nanometers, so that's 380 times 10 to the minus 9 meters, up to red light, which is 750 times 10 to the minus 9 meters. And we're asked A, what are the frequencies associated with these two wavelengths? So in order to do this, we're actually going to need to use the equation from the last topic, V is equal to F lambda. And because this is light, we know that the velocity is the speed of light, which is often written as c. So we know that the frequency is equal to c over lambda. So we need to do this for the violet light and also for the red light. So F for violet is equal to c, which is 3 times 10 to the 8 meters per second over 380 times 10 to the minus 9. And solving this one on the calculator, we end up with 7.89 times 10 to the 14 hertz. And then the frequency for the red light is equal to 3 times 10 to the 8 meters per second over the 750 times 10 to the minus 9 meters. And solving that one on the calculator, we get 4.00 times 10 to the 14 hertz. Now in part B of the question, we're told when light passes into glass, the speed of light is reduced to V is equal to C on N, where N is a refractive index and it is equal to 1.5. And we're asked what is the approximate speed of light in glass, and so this is just equal to 3.00 times 10 to the 8 over 1.5, and solving this on the calculator, we get 2.00 times 10 to the 8 meters per second. And then part C, if the frequency of light does not change when light enters glass, the wavelength must change to account for the reduction in speed. And we're asked what are the wavelengths for the two ends of the visible spectrum in glass. So once again, we're going to have to use our equation, V is equal to F lambda. We've calculated V here, and we've calculated the frequencies up here. So we know that lambda for violet light is equal to the velocity over the frequency for violet light, which is equal to 2 times 10 to the 8 over the frequency, which is 7.89 times 10 to the 14. So solving this one on the calculator, we get 2.53 times 10 to the minus 7. So let's give this in nanometers. This is 253 nanometers. And then for the red light, lambda for red is equal to V over F red, which is equal to 2.00 times 10 to the 8 over the frequency of red light, which is the 4.00 times 10 to the 14. And solving this one on the calculator, we get 5.00 times 10 to the minus 7, so that is equal to 500 nanometers. Problem 2. In this problem, we're asked if you want to view your full height in a plane mirror, must the mirror be as tall as you are? Explain using a ray diagram. Well, you probably know from everyday experience that the plane mirror doesn't have to be as tall as you are, as long as it's far enough away. So let's show that with a ray diagram. Here's you. We'll draw, here's the floor, and let's put some mirror here. Now, in order to see any part of yourself, light has to be able to travel from that part of you to the mirror and be reflected back so that you can see it. So let's draw your eyes here, about halfway down the height of your head. And now let's consider some light rays coming from some different parts of your body. Okay, so first of all, your feet. If we want to see light from your feet, it needs to go to the mirror where it needs to obey the law of reflection. And so we know that the angle of incidence has to be equal to the angle of reflection. So it's reflected off the mirror back to your eyes. So in this case, you can see your feet. Now, the other extremes on your body, let's just check. Let's check if you can see the top of your head. Top of your head needs to go to the mirror, and then it's reflected such that the angle of incidence is equal to the angle of reflection, and it can get back to your eyes. Okay, so this mirror is shorter than you are, and you can still see all of your body in the mirror. Let's consider a few of the limitations. Let's say that you were here. How would we want to position the mirror so that you could see all of your body? If you put it up here, then light can be reflected from the top of your head and go back to your eyes. If it gets reflected off the bottom of this mirror here, then using the law of reflection, it has to go up here. So with a mirror like this one, where you can see the top of your head, you can't see your feet. So there is a limit to how big the mirror has to be. So this shows that you can't see all of your body in all mirrors. What you can see depends on the distance of the mirror from your body and also the size of the mirror. This is problem 3. We're told that a laser beam is shone onto a mirror at an angle of 40 degrees to the normal as shown in the diagram. The laser is located 2 meters in front of the mirror and 3 meters above the floor. And in part A, we're asked what is the angle of reflection of the laser beam. Well, that bit's easy. The angle of reflection is in here, and our law of reflection tells us that the angle of incidence is equal to the angle of reflection. So this angle of reflection is just equal to 40 degrees. Now in part B, it says how far in front of the mirror does the laser beam strike the floor. So what we're trying to find is this point here. So let's label this length along here, length X. So if we can find X, that will be the answer to our problem. So in order to do that, we're going to need to use a bit of geometry. Let's label this part here Y1. So that's the top of the mirror to where the laser beam hits the mirror, and we'll call this Y2. Now to calculate Y1, we'll need to use trigonometry and just start off with some geometry. These two lines are parallel, so these are alternate angles on parallel lines, so that's 40 degrees up there. The other way to work that out is that this is 90 degrees, so this angle in here is 50, this angle up here is 90 degrees, so 90 plus 50 plus whatever this angle is has to be 180 degrees because it's a triangle, so that tells you that that is 40 degrees as well. And now we can use trigonometry, SOHCAHTOA. We know this angle, we know the adjacent angle, and we want to find the opposite, so we'll use TOA, and so we know that tan 40 is equal to opposite, which is Y1, over adjacent, which is 2.0. So solving this tells us that Y1 is equal to 2.0 tan 40, which is equal to 1.678 meters. Now, y1 plus y2 equals 3 meters. So we know that y2 is equal to 3 minus 1.678 meters. So y2 is equal to 1.322 meters. And now what we're trying to find out is this x. So we've got that this is 40 degrees here. So by exactly the same reasoning as up here, we know that this angle in here is 40 degrees. And so we've got tan 40, using TOA again, opposite, so that's y2 over adjacent, which is x, and so x is equal to y2 over tan 40, which is equal to 1.322 over tan 40, and so just solving this on the calculator, we get 1.575 meters, and then this is two significant figures. Everything here is two significant figures. 40 degrees is either one or two significant figures, so we'll assume it's 2. So this gives us 1.6 meters. Problem 4. In this problem, we're told that the diagrams shown, we've got one of them here, but are drawn by a student studying ray tracing. The student has sketched the position of the object and the direction of the rays are travelling from the mirror towards the observer. For each diagram, determine whether or not the illustrated situation is possible. If it is possible, draw the location and orientation of the plane mirror onto the diagram. Now we're going to need to use trial and error to answer this. So let's start by extending these rays back so that we can find out more about where they're coming from. Now the light has to come from the object, so let's draw the light coming from the middle of the object, and it'll be reflected off the mirror at some point along this extended yellow path here. So let's assume it's reflected at that point. Now if it's reflected at that point, we know that the angle of incidence is equal to the angle of reflection. So the normal to the mirror is going to be something like that. So let's use that to now draw on our mirror. So we can measure 90 degrees there, and that would be our plane mirror there. Now what we need to do is check if this works for our other eye as well. In this case, the light comes from the mirror to this point. We can draw our normal up here, and now we need to check and see if that normal is making 90 degrees with the plane mirror. So just use your protractor or a straight edge to measure it. That one's almost 90 degrees. If this wasn't right, we'd need to repeat that process again until we got one where the angles measured here and here were both 90 degrees. So let's just label everything here. So this is the plane mirror. This is the reflected ray. Both the yellow rays are reflected rays. This is the incident ray. And this pink one is the normal. And the same colours are the same thing for each of those eyes. Okay, now here's our second case. Let's once again extend back these rays. Now, in order to view this object from this first position, that would be one option. If this was the case, we'd have to have the normal halfway between those two, so something like that. And so we would have our mirror along here like this, in which case this would be our normal here. And that actually is very close to 90 degrees. So that has worked for that object as well. So we can find a mirror such that we can view these objects from these locations for both these situations. And the blue mirror shows that possibility. This is problem 5. Now in this first case, we have a plane mirror. To work out where the image is for a plane mirror, we're actually going to need a couple of observation points. So let's add an additional observation point. There we go. And now what we can do is we can trace rays from these two eyes. In order for the light to arrive at this eye, it needs to travel from the object and be reflected off the mirror such that the angle of incidence equals the angle of reflection, and then arrive at this eye here. So this eye interprets the object as being back along here. Let's also extend our normal back behind the mirror. And now this second eye, In order for it to see light coming from this object, light has to come from the object, bounce off the mirror such that the angle of incidence is equal to the angle of reflection, and arrive at that eye. So the eye interprets that light as coming from behind the mirror. So you can see the image is going to form where these two rays cross, so back here. And if you've drawn it really accurately, then this and this should have exactly the same size. So when I printed it off, this was 7 millimeters, and this one here was also 7 millimeters. So the magnification is equal to 7 over 7, which is equal to 1. And it's the right way up, so there's no negative sign there. Now this is a virtual image, as the light rays don't actually pass through this point. It's just that we interpret them as having passed through this point. Let's go on to the next diagram now. So in the next part of this problem, we've got an image like this. Now in this case, this is a cave shape, and so this is a concave mirror. Now we need to draw our rays. In this case, with a concave or a convex mirror, we draw two rays. The first one we draw parallel to this principal axis, like this, and then when it's reflected off the mirror, it goes through the focal point of the mirror like that. We draw the second ray going through the focal point to the mirror, and then when it's reflected so that it is parallel to the principal axis. And so you can see that the image is going to be formed at this point here. So this is our arrow going down here like this. Now when I printed off this PDF and measured the heights of these things, this was 7 millimeters and this one was 1.6 centimeters or 16 millimeters. So that tells us that the magnification is equal to 16 divided by 7, and the image is upside down, so we've got a negative sign in there. And so that gives us minus 2.3 as the magnification. Now the rays really do pass through this point, so this is a real image. So let's have a look at the next one now. Okay, so in this next one, this is once again a concave mirror. And once again, we use the same process to draw on our rays. We draw one ray, which is parallel to the principal axis, like this, and then it's reflected off the mirror so that it goes through the focal point of the mirror like that. And then with our next ray, we draw it going through the focal point. Then when it is reflected off the mirror, it travels parallel to the principal axis. So that is like that. Then it forms an image. The image is here, so we can draw our arrow like that. This is a real image because the light rays really do pass through this point. So now calculating the magnification, that's the image height. When I printed this, I got that this was 4 millimeters high and this one was 7 millimeters high. So the magnification, this is upside down, so it's negative 4 on 7, which is about equal to minus 0.57 as our magnification. And let's now look at the last situation. Okay, so this is our final situation. Now in this case, the mirror is curving this way and our object's on this side, so this is a convex mirror. Now once again, we need to draw our two rays coming from the object. So we draw one which is parallel to the principal axis. Now when it's reflected, it is reflected so that it would have come from this focal point behind the mirror. So it's reflected up like this. We draw our next principal ray going through the focal point, but then when it hits the mirror, it is reflected parallel to the principal axis, so along here like this. Now you can see on this side of the mirror, these rays are diverging, so we're not going to get a real image. What we're going to need to do is trace these rays backwards and where they cross is where we're going to interpret this image as coming from. So that's this point here. So let's draw our image here. So then we can use a ruler to measure this. When I printed it off, this was 7 millimeters and this was 4 millimeters. So this is a virtual image, as the rays do not actually come from this point here. So the magnification is equal to the image height, which is 4 millimeters, on the object height, which is 7 millimeters. So this is equal to 0.57 in this case, and it's positive as the image is the right way up. So problem 6. In this one, we're told that a small bulb is placed in front of a convex lens. In part A, which we've got here, we're told, suppose that the bulb is placed as shown. Using all 3 principal rays, draw an accurate ray diagram to determine the location of the image. So the first thing we want to draw is to draw our line through the middle of the lens. There we go. Now you should check with your protractor when you draw this line that it makes an angle of 90 degrees with the principal axis, which is the dotted line there. Now what we need to do is draw each of the 3 principal rays. Now the first principal ray we have to draw parallel to our principal axis. So with your protractor, make sure that it makes an angle of 90 degrees with this line that we've just drawn here. And now as it's the first principal ray, once it gets to this point, it is refracted up through this focus here. So let's draw it like that. Now, the second principal ray travels from this focus through the bulb until it comes to the lens. So we draw a straight line like this, at which point it is refracted so that it travels parallel to the principal ray. So again, make sure that these angles here are both 90 degrees. And the third principal ray travels directly through the middle of the lens and keeps going in a straight line. Now you can see on this far side of the lens that they're all diverging. So we need to find out where they cross each other in order to make the image. So we will trace them back and find out where they cross on the other side of the lens. So that will be where the image is. So we draw these lines. Hopefully they all cross at about the same point, which they do. If you've drawn it very accurately, they will all cross at the same point. So this location here is where the image is formed. Now, before we go on to part B, let's just answer part C for this question. Part C says, suppose that in each of the above cases you were to place a small paper screen at this image location. What would you see on the screen in each case? In this case, we would see nothing because this is a virtual image. So the light rays are actually diverging like this, and it's just our brain that interprets the image as being back here. And so virtual image and it does not project onto a screen. Okay, so this is part B. In this case, we're asked to repeat part A, but now the bulb is further from the lens. First of all, let's draw our line through the middle of the lens, making sure that this line is 90 degrees to that principal axis. Okay, now the first principal ray comes along parallel to that principal axis, so that we're making an angle of 90 degrees with our lens, at which point it is refracted up through the focal point. The second principal ray travels through the focal point on this side of the lens from the object, at which point it is refracted so that it goes parallel to the principal axis like this, and then the third principal ray travels right through the middle of the lens and keeps going in a straight line. And so you can see that we get an image formed at this point here. And so part C to this question, if we were to put a screen here, an image would appear on the screen. It will be an inverted image. But it will be real, as the light rays do actually pass through this point here. This is problem 7. In this problem, we're told to use the 3 principal rays to determine the location of the image of the object produced by lens 1. So to start with, let's draw our line down the middle of lens 1. Now you should make sure with a protractor that this is exactly 90 degrees. And now we need to draw our 3 principal rays. So let's draw the first ray. It travels parallel to this principal axis. Once again, use a protractor to make sure that it's making an angle of 90 degrees here. And then once it hits the middle of that lens, it is refracted through this focus here. Now our second principal ray goes from the object through the focal point on this side of the lens until it hits the lens, which is right there at an angle of 90 degrees, and then it's refracted parallel to the principal axis, and finally our third principal ray goes right through the middle of the lens like this. And so you can see that the image is going to be formed here, and the light rays really do pass through here, so this down here is a real image. Now the question goes on, part B, treat the image produced by lens 1 as the object for lens 2. So use 3 principal rays to determine the location of the image of this object produced by lens 2. So what we need to do is start by drawing our line right through the middle of lens 2. This needs to be 90 degrees, make sure that's accurate. And now we draw our principal rays. So the first principal ray travels parallel to the principal axis, and then when it gets to the lens, it's refracted up through this focal point. The second principal ray goes up through this focal point until it hits the mirror, which is way up here, and then it travels parallel to the principal axis, so like that. And then the third principal ray travels right through the middle of the lens. So we just need to extend. We didn't draw this line quite far enough. Extend it, and hopefully they all cross at the same point, which they do just about. So if you've drawn it very accurately, then they will all cross at a point. So this is the image, and the light rays really do pass through this point. We haven't had to trace them backwards, so this is a real image. So you can see this is providing a lot of magnification. It's with these 2 lenses here, we have the images the right way up, but very magnified. Okay, part C, we need a new diagram. Now we're going to repeat the same process, but you can see now lens 2 has been replaced with lens 3, which has a slightly longer focal length compared with lens 2. Let's start the same way by drawing the lines through the middle of these lenses. And now we can trace out our principal rays. So the first principal ray travels parallel to the axis and then goes through the focal point And as this is the same lens, we should get the image formed in exactly the same place as we did last time. So you can see the image once again is here. Now we trace our principal rays again, parallel to the axis, and then through the third focal point. Now in this case we go through the focal point, through the object, and then parallel to the principal axis, and then we go from the object parallel to the principal axis. Now you can see on this side of the lens these are diverging rays, so they're not going to come together and form a real object on this far side of the lens. So what we're going to need to do is trace these rays backwards and find where they cross. Let's trace them backwards in yellow. 1, 2, 3. And if you've drawn it really accurately, they will all cross at exactly the same point. So this is where the image forms. This is a real image. This is a virtual image, as the rays don't actually pass through this point. Problem 8. In this problem, we're told that in lectures we talked about glasses that made objects appear upside down. What shaped lens could achieve this, and what would you want the focal length for these lenses to be? Just estimate an order of magnitude. Okay, well, what we want to see is something which is upside down, and it's actually convex lenses which create an image which is upside down. So let's just show that now. Here's a convex lens. Now, what we're actually going to need is a really short focal length. So let's make this focal length here. So the focal length wants to be less than the length between your eye and the glasses, so maybe a few millimeters if possible. And now let's just check that this is going to cause us to see things upside down. So let's imagine here's a tree, and let's sketch the light rays coming from this tree. So we'll sketch the 3 primary light rays coming. Let's draw our line through the middle of our lens so that we can work out what's going. Let's draw a ray coming from the top of the tree, comes parallel to this primary axis, and it's then reflected through the focal length. Our second primary ray goes through this first focal point, gets to our lens, at which point it goes parallel to the principal axis, and then our third primary ray goes right through the middle of the lens and hopefully keeps going in a straight line. So this hasn't been very well drawn. These should all cross at the same point, but what you can see is the top of the tree ends up down here, and so we have an inverted tree. So if we're looking at it from somewhere like here, we're going to see an upside down tree. So the answer to this question is we want a convex lens with a very short focal length. Okay, problem 9. So what we need to do to start with is to trace on our primary rays. Now in this case we've got a diverging lens. So the first primary ray we draw parallel to the principal axis until it gets to the lens. And now the difference with a diverging lens is that it then gets refracted such that it appears to have come from this focal point. So we can draw it travelling up in that direction. So it follows the path here and then up here. Now for the second primary ray, we draw the second primary ray as if it was going through this focal point, the far focal point, but when it hits the mirror it is refracted and travels along parallel to the principal axis. And finally the third principal ray just travels so that it goes through the centre of the lens and keeps going. So you can see, as this is a diverging concave lens, it is diverging on this side. They're all moving apart. So in order to work out where the image is, we're going to have to trace these rays back, and hopefully they will all cross at the same point. And so we have traced back the first and the third, the pink and the green ones. We just now need to trace back this one, which goes parallel to the principal axis. And if we've drawn it accurately, it crosses at the same point, which it does here. So let's draw our image on here. Here's our image. So we've done part A, we've traced our primary rays. Part B says, is the image real or virtual? Well, this is a virtual image, as we had to trace backwards along the rays. The rays don't actually come from this point, it's just that they look like they do. And part C says to calculate the magnification. So that's using the formula given in question 5, which is that the magnification is equal to the image height over the object height. So when I printed this off and measured it with a ruler, I got that my image was 2 millimeters tall and that my object was 6 millimeters tall, which gives me 0.33 as the magnification. And that's a positive number because it's the right way up. Problem 10. We're told an insect is embedded inside a block of glass. Okay, so we've got some block of glass here, and here's our insect. The insect is located 2.4 centimeters below the surface. Okay, so this length here is 2.4 centimeters. Let's call that length O because it's the length of the object, which in this case is the insect below the surface. And we're told that this is in glass with a refractive index of 1.5. And we're asked, how far below this surface does the insect appear to a person looking at it from above? Okay, so let's draw a few rays. Here's a light ray going from the insect to the surface, and here's another one. And now let's draw the normal to the surface. Now when the light ray moves out, it makes a larger angle with the normal like this. So let's label these. Let's call this one theta O, theta for the object, and then this one here we'll call theta I, so theta for the image. And now what our eye imagines is that rather than bending, our eye doesn't realize that the light bends, our eye interprets this line as coming back from here, and if we do the same thing on the other side, our eye imagines that this insect is actually at this point here. So let's label this distance here I, and this angle here, if that was theta I there, this angle in here is theta I. Okay, so what we want to do is work out what's I. That's what the question asked us. Now, in order to do that, we're going to need to do a little bit of trigonometry. Let's call this length along here x. Now we need to do a little bit of geometry. This is 90 degrees here. If this angle here is theta O, then this angle in here is 90 minus theta O. So this angle down here is theta O. And so we've got O and x, and we have tan theta O is equal to opposite. This is from SOHCAHTOA. Tan theta is equal to opposite, which is x over O. And so this tells us that x is equal to O tan theta O. And now let's do this other triangle here with I. this angle here is theta I, so this is 90 minus theta I, and this angle here is theta I. And so we've got tan theta I is equal to x on I, and so x is equal to I tan theta I. But both these things are equal to x, so they must be equal to each other. So O tan theta O is equal to I tan theta I. Okay, now we have to use a little bit of maths. For small angles, which we're assuming this is, the insect isn't really very big compared to the 2.4 centimeters. So if we assume theta is small, then tan theta is approximately sine theta. And so we've got O sine theta O is equal to I sine theta I. And so I on O is equal to sine theta O over sine theta I. And now we can use Snell's law. Sine theta O, that's the angle of incidence in the medium with n equals 1.5. So we can call this, so we know that this is n of the glass down the bottom, because we have sine theta 1 on sine theta 2 is equal to n2 on n1. So if we have this is inside the glass, then we need to have the glass down the bottom. Now this theta I, that is the angle of refraction, which is in the air. So this n is the n of air. So we have I is equal to O times n of air, which is 1 over 1.5. And so this is equal to 2.4 centimeters over 1.5, which is equal to 1.6 centimeters. Question 11. In this question, we're asked an LCD screen uses red, green and blue pixels in order to produce the colours that we see. In printing, however, we use magenta, yellow and cyan as primary colours. How do these two situations differ, and explain? Okay, so on an LCD colour, what we're seeing is the projection of actual light. So they want to stimulate the actual colours which will arrive on our cones and stimulate those cones. So on an LCD screen, these three colours all stimulate our cones. And adding more colours adds to the colour that we see. So for example, red plus blue, what we see, wavelength, blue light has a shorter wavelength, so it's something like that. And then if we add some red as well with a longer wavelength, it's like this. And our brain interprets this as magenta, a kind of purpley colour. We interpret it as a mixture of blue and red. On the other hand, in printing, the colours reflect light. So adding more colours reduces the amount of light that is reflected. So for example, if we have magenta ink, which reflects the blue and the red wavelengths, and then we add cyan. So cyan, this is blue plus red. Cyan reflects blue and green. Then when we add these two together, they only reflect the colour that they have in common. So in this case, these two only reflect blue. And so this is how we get the blue colour in printing. In this case, we've got what's called subtractive mixing. As it's only the colours in common that are reflected, whereas this is called additive mixing, as when we add more colour, then we see more colour. So if we were to use all three colours on an LCD screen, it would look white. If we were to use all three colours in printing, it would look black, as very little light would be reflected.